All right. Hello, everyone. Thank you for coming and joining me here today. Today, I want to share a couple ideas and lessons learned from my expertise in doing machine learning consulting, and basically some ideas I've learned on how to accelerate R&D and get to production a lot faster. Really quickly, before I get started, a little bit on my background. I'm the founder of Scalar Research, which is a machine learning consulting firm, and I work very closely with Toptal, which is a talent network for software engineers, data scientists, and more. Before this, I also spent a number of years at the Stanford AI Lab, where I conducted research on computer vision, and particularly applications in the healthcare space. But throughout my experience in consulting for machine learning companies, one of the things I learned is that there's a very big lack of tooling for data scientists to actually get their work done, particularly in the R&D stage. People are often used to very good tooling for software engineers and product managers and so on. But when it comes to data science, and in particular some of the more recent methods of doing data science, the tooling is still pretty lacking. A second problem here too that we have, and this is actually a pretty big challenge for having good tooling for data scientists, is that the tooling needs to know a lot about the infrastructure that you're working with. And like a lot of the software engineering tools, often data scientists, they actually need to use servers, need to use maybe a cluster of servers, deal with massive data sets and so on. And this is actually a big challenge when it actually comes to developing good tooling for data scientists. And then finally, a lot of the tools that we have right now, they're very focused on the DevOps side of things. So on deploying this in production, actually getting models to work, or training at scale and so on. But when it comes to the day-to-day of data scientists or the R&D stage, that's still pretty lacking. We have a lot of DevOps tools, but very little dev tool solutions here. So I wanted to show some of the many issues I came across, and one of them, dive deeper and actually discuss some of the solutions we were able to implement and accelerate this stage. So I want to focus a little bit on the workday of a computer vision engineer, see some of the bottlenecks that they come across, and from there explore a solution that actually helped accelerate the R&D stage for this project by quite a lot. So if you're a computer vision engineer, you're often working with a very large data set. So for example, you're working with days of data of 4K video. This could be terabytes of video data. You need to extract a lot of frames. This could be millions or tens of millions of frames of images, especially if you're working with high FPS. Then you need to process all those millions of images. You need to rotate. You need to crop and apply a number of other pre-processing steps. And then finally, once you have pre-processed all those millions of images, you can start doing your actual computer vision work. And even at that stage, the computer vision work itself is actually compute intensive as well. So, but as you're working through this pipeline, if you're working with millions of frames on a single server, this can often take up to a day or even more to pre-process all this data. So the problem that we have is that if you try to use one of the production-grade solutions out there, let's say Airflow or a comparable pipeline solution, a problem you're going to come across is that if you're working this very early R&D stage where you're doing a bunch of experiments every day, and often this is the case for data scientists, you're trying different data sets, different solutions, different algorithms, and so on, actually setting up a proper, by traditional standards, pipeline solution, that's going to add a lot of overhead, and you're not going to be able to iterate very quickly. So, and in addition to this, as you're setting up this infrastructure, especially if you're a data scientist, you're often not very familiar with the latest DevOps solutions. You're not a DevOps expert, so it's actually a pretty steep learning curve to expect the data science team to set up a DevOps infrastructure for the actual experiments that they're building. And then, especially if they're doing this in a way that they're not the best experts about, that adds a lot of overhead for them, and the cost can be pretty big. And then finally, all those tools, like I mentioned, they're focused on the very mature pipeline. So if you want to deploy to production, if you want to have, let's say, a very large trial proof from users and so on, but not if you want to iterate very quickly. So what happens in practice, what I've seen internally for myself and for other external data science teams I've worked with, is that they basically skip working with those tools altogether, and they're set up pretty much like copy-paste solutions all the time. So they're copy-pasting pre-processing functions from previous pipelines that are pretty similar. They're taking from different projects, open source libraries, and so on, and kind of just meshing them together. The main problems that we have with this is that first, it's usually very inefficient. You're doing like a single-threaded solution on a single server, and if you're working with those massive data sets of terabytes of data, that could be very slow. The second problem, too, is that optimizing the code doesn't really help this, because even if you have, let's say, a multi-threaded solution on your own server and it works very quickly, in a lot of cases, you can reduce the processing time from, let's say, a couple days to several hours, but it's still something that's very slow. So ideally, you'd have something that works with a lot of infrastructure at scale and can deploy several servers and process things in a very parallelizable way very quickly. And then finally, a very big issue that we have when you do something like this is that if you're copying pasting all those solutions and all those functions from different libraries and from previous projects and so on, what happens is that those functions don't actually always fit together. So it might be the case, for example, in computer vision, one function is expecting an RGB image, another one gets an BGR image, so they don't really fit together, and if you just copy paste them and don't have proper testing and so on, which is common in this very early R&D stage, you're going to come up with a bug that often only surfaces at the very end after several hours of processing here. So this is a very common problem that we have. There are several issues that data scientists are facing, but this is one of the very commons that I see. So one of the solutions we developed internally for one of the projects was to actually create a data pipeline that's focused on the R&D stage. So we had before we started, we had a couple guiding principles. First is that we wanted to create something that would be very low overhead and very easy to learn. The idea is that if we created something that was similar to Airflow or one of those other solutions, it would have very little usage by the data scientists, it would have a huge learning curve, and likely it would also be the case where they wouldn't actually use this in a day-to-day. The second thing we decided to really focus on is to, from the start, focus on massive parallelism. Like I said, even if you really optimize your code and get like a very large server, often it takes several hours to process a data set on a single server. So the idea here is that we want to leverage a very large number of servers instantly and finish the task very quickly, and then do this also in a way that we can scale up very quickly, do the computation very efficiently in this elastic way, and then scale down very quickly. And the idea is that we wanted to do this such that the overall cost would be about the same in terms of computational time in aggregate, but do this in parallel to really speed up this R&D process. And then finally, we wanted to make this in a way that would fit the production very well. One of the problems you often see is that if you have a completely different stack for R&D and production, some of the times that can introduce bugs, and especially where data science, where small modifications in the data set or pre-processing and so on can lead to major differences in the outcome. If you have two completely separate code bases, you might not actually get the same result. So we wanted to use something that could easily go from what we were using in production to actually R&D and back and forth. So the idea here is that the UX that we wanted to have for the practitioners was very simple. We wanted to define the inputs that could be, let's say, an S3 bucket where all your images or videos and so on are lying. Then you have some set of transformations that could be like a Python script or something similar that you're going to use to apply to each of those data points. And then you're also going to specify where the output of those computations to go. And I'm going to show a very simplified version of kind of like the pseudocode of how this whole system is architected to get to an idea of what we're trying to achieve. So the first idea here is that we wanted to just package the pre-processing function on a single data set. So the data scientist doesn't have to focus on multi-threading or anything like that. It was just something that works on a single data point. And we can basically wrap that around in a function that pretty much takes a single data point from disk that we pass, then the data scientist applies whatever transformation and writes that to disk in something we specify. So that's all the data science actually has to do. And then for the data scientists themselves, then they can call this function using, like I mentioned, the input and output sources of data. And then for the data scientist himself, that's the actual work. And then behind the scenes, using the functions and the tools we build, we're first adding a step that wraps around this functionality, this pre-processing script. Basically, we load the whole data set from the data store. We're going to download, let's say, if it's a massive data store where we're going to use multiple servers, like different batches and so on, we're going to split that into a way that's reasonably optimized for multi-processing. So we're going to spawn multiple versions of those pre-processing scripts and pass the corresponding data points. And then once we saw the result, or if it timed out or something like this, we're going to write the outputs to, again, to S3 or a different data store, and write the logs to an external logging solution. And finally, like I mentioned, that worked at the level of a single server. And then we have a different module that's basically an orchestrator that applies that to multiple servers. So we're going to take this whole data set and split into as many servers or Lambda functions or whatever there might need to be, and actually coordinate between making sure we have all the different results. If anything times out, we can retry, and so on. And basically, at a high level, this is what worked. And actually, we were able to then take a single, simple pre-processing script and basically having these multiple layers wrapping around it with very little customization by the data scientists, actually have it work at scale of several servers or by hundreds or thousands of Lambda functions and so on, and have the results very quickly in a cost-effective way. So in terms of the outcome, like I mentioned, this increased the productivity by a substantial amount. It could go from pre-processing in the scale of hours or days to often minutes, since we can use, let's say, 1,000 servers for a couple seconds each. The second positive outcome here is that this was also very easy to implement. So for a data scientist, the overhead of actually running the script compared to, let's say, a more traditional data pipeline solution, this was a lot simpler. So the internal adoption and the retention from the partitions were actually very good. And then finally, once we have this whole infrastructure, we can actually go beyond just scaling the processing time of the data sets. One of the interesting things we can do is actually validate the data online. So the data scientists can add a lot of checks for the data. For example, we should expect images to have this resolution or this sort of dimensions and things like that as they're going for the different steps in the pipeline. And we can detect the problems very early on. So if we see a job where, let's say, different functions didn't fit together or there's some early problem, we can detect that in the initial runs. And if that fails, we can stop the results right away. And the data science can reevaluate that, looking at the logs and so on. And we don't waste several hours to actually get the outcome of the batch and actually only then be able to diagnose what happened. The second interesting idea here is that we can use this to build a lot of building blocks and reuse those building blocks, like I mentioned, using the best practices. So, for example, in a lot of cases, the simple way to load an image or a video or extract frames, that's the way most practitioners are doing, since it's just like a one line of code and so on, but there are more efficient ways of doing so. And if we use those building blocks and let them reuse them across those pipelines, we can speed up development also by a lot more, and also do that in a more efficient and more cost-efficient way. And then finally, we can also use those tested and reused blocks in production very quickly. So like the code for pre-processing a single data point, that's actually pretty similar to what it would work in production. So we can quickly translate that from this early R&D stage where you're experimenting very quickly and shift that to a production setting where it's also tested, it's using the best practices and so on. And then finally, on the more data science side, this also helps with, for example, doing more efficient data sampling. So if you're working with a large data set that has, let's say, different classes, that has, for example, temporal data, we can use some of the functionality we've built to sample that way more efficiently. And basically, if you're working with a subset of your data set, you can get a meaningful subset for training and so on. And then once you're sampling this interesting subset, you can actually look at some of the properties of the data set to ensure you're getting the results you want. So for example, you could analyze the distribution of certain variables or certain properties of the data points. If you see any problems that change per class and so on, you can notice that very quickly, and then that simplifies this sort of exploratory data analysis work by the data scientists. So basically, in conclusion, the idea we saw here is that the tooling that we need for development, so dev tools, is actually very different from the needs from like a DevOps perspective. And in practice, there's been a lot of focus on the DevOps, but actually spending some resources on creating this sort of dev tools actually was able to increase the productivity of the team by a substantial amount. This is what I wanted to cover. I'm happy to answer any questions by email or later outside. Thank you.